So event extraction is an amazing topic in text mining and natural language processing. And so I should say that there are two types of paradigms for event extraction at the sentence level, like classical event extraction that we think about just a single sentence and identifying the triggers, only one trigger and its attributes. But there is another type of event extraction which considers also the intra events. I mean, it also models the relationship between different triggers because you may have more than one trigger and they have some interaction and intersections as well. These are amazing articles in 2011, Event Extraction as Dependency Parsing. So Christopher Manning showed us that we can think about it. It's like, why is it like dependency parsing? Because dependency parsing is the relation between two words. What is the relation between two words? And event extraction is exactly the same, but the labels are just different. You can think about it just like a graph, but the labels are different. Instead of a modifier and those things that we use for dependency parsing, we have a different set of labels. And in some cases, it is even more difficult than dependency parsing. And we don't have enough supervised data for that as well. There are lots of challenges that we have to deal with. There are other interesting articles like this one in 2018 or event extraction using distance supervision. This is really important. And within a document, at the document level, we are talking about more than just one sentence. We are not talking about a traditional event extraction, which is very easy. So what is event extraction? Rainfall in July continued in Ethiopia and causing displacement. So we have a pre-processing tagging named entities. People do it, classically do it independently. But what is important is to add all of these losses so that we train them jointly, because the text is rich. So we should think about it like the way human understand the text. So we consider everything at the same time simultaneously. An event extraction, so we can think about it traditionally as an event detection, detect and classify the event mentioned, and also argument extraction. So what is event extraction? We have a set of events, live movement, transaction, and we have some event subtypes, for example, be born, marry, divorce, but we collapse sometimes all of them to just single one because we don't have enough data for each of these. So it's a good idea sometimes to collapse if you have not enough training data. And so the AC event ontology, as I told you, is like live, business, different events. And so in your language, you can define your own set of categories. Another example is this. For example, event schema. It is conflict, and it has some argument roles such as target, instrument, time, place, or if we have an event, different event types such as transfer money, we have different argument roles. And the event extraction, for example, this example, you have a type, so the trigger is what is inside the text, but the type is what we associate it with. For example, we associate attack with the conflict type or attack type. And we also have some arguments. So the ACE stands for automatic content extraction. It's an expansive dataset, like the universities can order that. And it's like that Penn State for dependency parsing. It is not free. And so what are event anchors? Many events anchors on a single verb or noun. For example, 6 murders occurs in France, including the assassination of Bob and the killing of Joe. There are some cases where multiple words could reasonably be called the trigger. You see, multiple words. So we can choose a word as the anchor. So this is an anchor. Event 1 is murders, event 2 assassination. You have different kinds of anchors. And what is important is nested event structure, because it's just like nested entity recognition that we do, all the techniques that we do for nested entity recognition, we can also use for nested event structure, because it could be very nested. So the idea is taking the tree of event argument relations and using it directly as the representation in a re-ranking. Oh, this re-ranking is really important in machine learning. We can improve our model one step, and we take the tree of relations and their arguments and use it directly as the representation in a dependency parser. So we first convert the original representation of events and their arguments to dependency trees by creating dependency arcs between event anchors. So this is some articles, nice articles about nested event extraction. For example, you see this is the trigger, reduced is the trigger, and the nested one is like this. You have 2 different triggers in one sentence. You see, they're 2 different, but they have some arguments, and so we say that this one is the theme for another trigger. Or here you see different triggers and their different arguments. So 2 events. So binding here is the cause of localization. This is binding, and this is the cause of this, and this is another trigger. So you see we have multiple triggers in just one sentence. In a nested event structure, so we have different relation types, cause and theme. And this is an example in this article of Christopher Manning, and you see that we can just convert it to event dependencies, and I will explain you the algorithm. So the nodes in the graph are protein entity dimensions, event anchors, and the virtual root node. For each event anchor, we create one link to each of its arguments labeled with the slot name of the argument. And finally, the output of this process is a directed graph, since a phrase can easily play a role in 2 or more events. And there are 2 questions for you to think about. How can we guarantee a result is a tree? Can you create some pruning algorithm to guarantee that? Or another problem, which is very hard, guarantee that the resulting tree is projective. So different paradigms, you can handle this problem in different paradigms. And in the next lectures, I will show you different approaches. So step 1 is we remove the self-referential edges. With step 2, we break the structures where one argument participates in multiple events. And step 3, we unify events with the same types anchored on the same anchor phrase. So how can you guarantee that the resulting tree is non-projective? Non-projective, it means that they don't cross each other, as simple as this. Because in parsing, we don't want them to cross each other. For example, this word is in the middle of these words. And because this is a sentence, we don't want this one to happen. So for recognition of event anchors, you can think about it as a multi-class classifier that labels each token independently. So at the token level, at the surface context, syntactic context, bag of word and entity count. And And final, parsing event structures. So given the entities and event anchors from the previous stages, the parser generates labeled dependency links between them. Many dependency parsers are available, so we just use minimum spanning tree parser, because the reason that I like spanning tree in computer science, because it isn't, even if your graph is very complex, you can also handle that, especially with the non-projective case. So just a quick review is dependency parsing, as I've explained in my playlist on dependency parsing. So we have order of n squared edges, because we connect each of these two to each other. The same thing you can use for event extraction. So the features that we could use is either unigram, bigram, in-between part of speech features, surrounding words. So the same kind of features that we use, we can use a different set of features for event extraction. And finally, the score is just this is the weight, and these are the features. And just like dependency parsing, you have a score. The goal is finding the weight. This is the weight vector. So there is an edge between the ice word and the J's word. We want to identify them. And just like CKY is dynamic programming for inference of a constituency parsing, here Jason Eisner has invented a very similar algorithm for, it's like CKY, but for dependency parsing. So we can understand what is the direction between two words. So it's a bottom-up strategy, going from bottom of the tree to the top of the tree. So you see, at the inference, we always need a kind of dynamic programming. For example, CKY, Eisner, maximum spanning tree, or we can use shift reduce. The reason that people use it, because they are not the order of complexity is too low, and that's fantastic. But the problem is it cannot handle complex sentences. So dependency parsing, we have chart-based algorithm, the algorithm of Eisner, and shift reduce, and graph-based that uses minimum spanning tree. And the discriminative re-ranking, there are two articles that I really like, because they are fundamental. Many articles just refer to these amazing articles, and I think that's it.